Today I am going to present about the multi-streamed solid-state drive. Well, these days storage device is moving from hard drives to SSD. One of the biggest reasons is that SSD shares a common interface with the hard drives. So such a common interface avoids tremendous overheads migrating hard drives to SSD. But as you know, the nature of the device is totally different. Unlike the traditional rotating media, SSD has NAND flash memory, which is organized into pages and blocks. Data in NAND flash memory is erased at the page level, written and read at the page level, and erased at the block level. So presenting logical block addresses makes sense for hard drives, as their sectors can be overwritten, but it is not suited for the works of NAND flash memory. So flash translation layer is implemented in the SSD controller to emulate the hard drives and exposes logical blocks to upper level. FTL has two main purposes: logical block mapping and garbage collection. Since NAND flash memories does not allow user data to be overwritten in the same memory page, I said they should erase old data before writing new data. This is garbage collection. So in more detail, garbage collection is the process of relocating existing valid data to new block, and then erase these blocks for new data to be written. So such a valid page copying and erase operation have a large impact on the SS lifetime and performance. So if we use SSD longer and longer, there will be lots of valid pages to be copied. So for an example, I will show you the Cassandra update throughput in the SSD system. So as you can see, the performance of SSD gradually decreases as time goes on. The main reason of the performance degrade is the increasing GC overheads. So GC highly affects the SSD performance. Therefore, we think on new interface for SSD. This interface should coexist with the existing block layer and should be general to all of SSDs and should have a concrete concept. So we proposed the multi-streaming interface, which guides data placement within the SSD for high GC efficiency. So by using our proposed interface, we can sustain Cassandra update throughput. So it actually improved over the traditional SSD. So in the rest of my talk, I will talk about the research background, and then I will introduce the multi-streaming interface and experiment results. Generally, to optimize the system, applications process data sequentially, because sequential I/O has shorter head movements than random I/O. However, sequential I/O is not always good on the SSD works. So take a look. Left example is applied sequential LB updates into block 2. So there are some embedded data in block 0 and block 1. So they are basically fragmented. The right example is applied random LB updates into block 2. So, and only block 0 is filled up with the invalid data. So clearly, future garbage collection will proceed more efficiently in the right example, because block 0 can be reclaimed quickly without copying data. So as you can see, random updates can be operated more efficiently in SSD. So SSD's GC overhead depends not only on the current write pattern, but also on how data have been already placed in the SSD. So to know how data have been already placed in the SSD, it is better to let SSD know how to write data. So we use a stream, which is an abstraction of SSD capacity allocation that stores data with the same lifetime expectancy. So we divide the streams according to their data lifetime, and data with the same stream will be placed into the same erase unit. So by using stream concept, we proposed the multi-streamed SSD. This multi-streamed SSD map data with different lifetime to different streams. So if a host provides information about the data lifetime using the stream ID, then SSD places data with the stream with the similar lifetime into the same erase unit. So multi-streamed SSD has a high GC efficiency. Now we basically compare the traditional SSD with the multi-stream SSD. In the traditional SSD, the data are written in blocks in order as they are requested. And blocks are fragmented. This is what we try to avoid it. If we use multi-stream interface, data are placed according to their stream ID. So it will reduce the valid pages to copied. But for effective multi-streaming, proper mapping of data to stream is essential. This means the host should know about the data properties exactly. For real implementation of our multi-streamed SSD, we choose Cassandra, which is well-known key-value store database. For mapping data, we analyze the Cassandra's write operations. I will quickly explain about that. Whenever data is inserted, data is written at the commit log and in memory as a mem table. And if mem table accumulates to the certain size, they flush it to the disk as a SS table. Since the SS tables are immutable in Cassandra, they are compacted periodically to a new larger size of SS table. So this compaction process reduces the space and time overhead for maintaining many SS tables. So this is size compaction strategy of Cassandra. So we take into account how data are created and destroyed in Cassandra when we map data into a stream. So this figure shows the write operation when Cassandra runs. When OS runs, OS writes something, such as metadata in journal. And Cassandra writes flushing data, commit log data, and the compaction data. So we map each write operation to different streams because we think that each write operation have similar data lifetime. The first mapping method is using just one stream ID. It is same with conventional SSD. Next, we separate the application write from system traffic. So we use two stream ID. One is for system data, and 0 is for system data, and 1 is for application write operation. Next, we further separate commit log from the Cassandra writes. So we use total 3 stream IDs. Finally, we gave distinct streams to different size of tiers of SS table when writing compaction data. So we completely separate every write operation into 5 different stream IDs. So we tested all these scenarios. We just sent down the test information. We used our product and run YCS benchmark on Cassandra using update only write intensive workload. And we modified the Linux kernel to pass the stream ID through the F-advised system call, and then the stream ID is stored in the inode of virtual file system. So this is the result of conventional SSD without the trim function. And when you trim on the conventional SSD, the performance improved and sustained at a certain level. But it is still far from the ideal. And when you use the multi-app, which is using 2 stream IDs, it's very similar to the conventional SSD. This is because the system data takes quite small portion of total I/O traffic. So when you use multi-log, we can get a higher performance. And finally, we can sustain the performance at a high level. And we also estimate the number of valid pages copied during GC. This is the result of conventional SSD without the trim. And this is the conventional SSD with the trim option. And this is multi-app, multi-log. And we finally, multi-data dramatically reduced the GC overheads compared to the other results. This throughput is very well correlated with the GC overheads. This figure presents the latency profile obtained from the previous experiments. The plot shows that multi-streamed SSD improves latency as well. So at 99.9%, multi-data lowers the latency by 54% compared to the conventional SSD. So in this paper, we proposed a special interface for SSD named multi-streaming, which is mapping applications and system data with different lifetimes to SSD streams. By using our proposed method, we can get a higher GC efficiency and lower latency. And our multi-stream interface can be supported on state-of-the-art SSD and coexist with the traditional block interface. And we hope our interface can be standard for using SSD more efficiently. And thank you for your attention.
Hi, thank you. Fred Douglas, EMC. I was wondering if you think your approach is specific to Flash, because it's reminiscent of some work from the first FAST conference from some folks at the University of Cincinnati called Wolf. And they had a thing for separating out things that they expect to have a longer lifetime from things that they expect to have a shorter lifetime and writing them to different places in a log structured file system, which had nothing to do with SSD, but it had everything to do with the kind of cleaning that you're doing. So do you think this is more general? And anyway, I thought you should be aware of that other work.
Actually, our interface is just added to existing block layer, so it is general to all of SSD and file system.
So I was wondering, you mentioned that you used the F-advise system call.
Yeah.
Did you have to modify Cassandra to add that? Or
No.
did Cassandra already have the F-advise in it?
F-advise call is you don't have to modify the Cassandra code because already they use.
It was already there?
Yeah.
Okay. And you didn't modify the SSD at all either? It was just this block layer?
No, we did not modify.
Do you have other questions? Okay, well.
Thank you very much.